Homework questions, anybody?
I promise I'll start on it tomorrow. Because you turned in that test today.
Yeah.
And anything from down there?
You're on mute. We always face that way, and the camera's actually over there,
Any
so
questions from down there? Okay.
I guess not.
Okay. All right. So we're looking. We might be able to have all the new material gone through by Monday. So then, so both versions of homework 4 are posted. You can pick which one you want to do, and basically, I need it turned in time to compute final grades to turn them in on the Monday after commencement, which is the 11th. I put 7th on the website because it's the last day of
So
final.
the 10th, right?
That is workable. That
would be a very
is the
stressful.
absolute last, latest I can do. So it's great to do like 11 a.m. then. Okay, so now we can keep going with QR iteration as it now stands. And we're just going to keep modifying it until it's practical. So what we have now is we take our matrix A and we perform a orthogonal similarity transformation to get a matrix that is upper Hessenberg. And then we repeat the following, that we compute its QR factorization, and then we override it by multiplying factors in reverse order. And what we arrived at last time is that for a Hessenberg matrix, QR factorization is especially cheap. We just use Gibbons rotations, row rotations, and then for the matrix multiplication of R and Q, we use Gibbons column rotation. So the same rotations that were used here on the left side, we use on the right side. So this whole part of the algorithm is order n squared, floating point operations per iteration, and we keep doing this until convergence. So what dilemma was addressed last time? The next thing we need to address is this part. How do we actually do that? How do we take a general square matrix A and reduce it to Hessenberg form using a orthogonal similarity transformation? So now I can describe the algorithm for that. Okay. And actually it's not hard to describe. So the Hessenberg reduction, which will be tridiagonal in the symmetric case. So starting with A, you apply a householder reflection on the left. And because it's similarity transformation, you must apply its inverse on the right. But householder reflections are their own inverses, so this is what we do. So this preserves the eigenvalues. And then we keep going, applying more householder transformations. And we're going to need a total of n minus 2 of them, because we need to zero elements in n minus 2 columns. The last 2 columns of the Hessenberg matrix are full. You don't need to do anything to them. And the result of this is Hessenberg matrix H. Now, what does each household reflection do? So each household reflection, right, so for your notes, this is a householder reflection. And its job is to equal to j plus 1, j plus 2, all the way to the end. So, because recall from before, a household reflection, its job is it can zero out all entries of a vector except one. So it's very destructive. Use some caution. So what it will do, actually, wait. Actually, j plus 2. That's what's going to zero out. Okay.
And the reason it's j plus 2 is because we don't want to get rid of our zeros that we already zeroed out, right?
Oh, no, it's because it would be j plus 1 if you were going for upper triangular
right.
form.
Okay. That's
Yeah.
fine.
Okay. So now what I can do is, now, so what this means is, if these are zeros we're creating, each household reflection affects rows and columns j plus 1 and down. Okay. And that point is very important because consider the first household reflection, P1. So P1 is going to zero entries 3 through n. So it's going to affect rows 2 through n when you apply it on the left. Then when you apply the same household reflection on the right, it's going to affect columns 2 through n, not column 1. So whatever damage you do in column 1 here to zero out entries is preserved when you apply it on the right. So that's why we have to go for Hessenberg form rather than triangular form, because that way your household reflections applied on the right do not undo the productivity you have from applying them on the left. Okay. So now I can describe this algorithm in a more MATLAB-like fashion. Okay. So I'm going to start by letting U be the identity, and I'll let my Hessenberg matrix, initially it's just going to equal A. And then I'm going to work on each column, going from left to right, as usual. I need the correct vector for a household reflection. So my vector V will be my householder vector working on this portion of the matrix. Entries j plus 1 down to the bottom in column J. And this gives me a vector V for my householder reflection. So it'll be identity minus 2 over V transpose V, V transpose. This V is not necessarily a unit vector. We're not assuming that. So that's why I divide by V transpose V. So this right here, 2 over V transpose V, that's just a constant, a scalar. So now I have the essential part of my household reflection, and for convenience, I'm going to form this constant here. I'll just call it C. Is 2 over V transpose V. And now what I can do is apply household reflections. So first I need to apply it on the left of H. So the portion of H that's going to be affected is, like I wrote on the previous board, rows j plus 1 down to the bottom, and columns j to the n, because in all previous columns the entries are already 0. Now, I'm not going to form this household reflection explicitly. I'm going to take this matrix here and distribute it. So I'm going to have identity times, so I'm just going to have this repeated. Okay, minus this constant times V, and then I have V transpose times this matrix again, this submatrix. Alright. I wrote a similar pseudocode for performing QR factorization using household reflections. The difference is this starts one row lower. Otherwise, the process is exactly the same as this. But now, for Hessenberg reduction, I have to apply the same household reflection on the right. So this right here does H is replaced by Pj times H. So now I'm going to apply to the appropriate columns. So all rows, and the same columns as I used as rows before. And for applying the householder reflection on the right, I'm going to have same constants, and then I have times V, and then times V transpose. So this line right here overwrites H with H multiplied by Pj on the right. Notice my parentheses here, and this is actually something to keep in mind as you, if you were actually implement this in MATLAB. By grouping these together, I'm performing matrix vector multiplication. I get a row vector, and then I have a simple outer product. On the other hand, if I had not used parentheses, it would have done this first. Outer product and then a matrix multiplication, and we don't want that. So, so sometimes how you group these operations, and matrix multiplication is associative, you can group them however you want. But how you group them does matter as far as efficiency. Here, it's going to associate this way anyway, but I figured I might as well make it explicit and do a matrix vector multiplication and then again an outer product. Those are nice cheap operations, or order n squared. So each of these lines is order n squared. The last thing I need to do, and actually I neglected to include this in my algorithm in the notes, is I need to update U. If I want my full surety composition, I need to form a product of all of these householder transformations. And that's going to work exactly the same as this line right here. So I can basically, I wish I could do a copy and paste and just change this. Instead of H, I have U. So I have U, all rows, these columns. That's it. So what this does, U is overwritten with U times Pj. So, so U is a product of all of the household reflections going from left to right. Okay. As you can see, this is going to increase the. There are two ways you can go with this. If you only want the eigenvalues, then you would not bother with this third step here. But if you want the whole surety composition, and therefore an opportunity to get eigenvectors, then you do need this. And you can see it's going to increase the overhead by 50%. So it's a key decision to make. Do you really want eigenvalues or not? Or eigenvectors or not? And if you're calling I in MATLAB, you can